Okay, we'll just get started. Um, okay, thanks for coming today on a Saturday for the second part of the lecture. The first part was covered by Zikun, I believe, and for the second part, I'll be doing it today. Yeah, so without further ado, let's just begin. Okay, so for today, we'll be covering code quality as well as refactoring, mainly implementation stuff. So for code quality, it's expected that you should code as though there will be another person that's coming after you to review your code. So it's expected that while coding, that you will use good coding practices. So we will look at some of them in detail in the next few slides. Okay, so the first part is to write clean code, meaning that clean code must obviously not have duplication. That's the first point. The second point is that it must be obvious for other programmers who are reading those code that come after you. So that means including comments, including JS docs, for example. So clean code must also have good test cases. So you must have a couple of test cases that is already written for you, in order to verify that the code actually works. And then you must also make sure that the clean code is essentially easy and cheaper to maintain because of the fact that it contains more documentation. So what we want to reduce while having good code quality is what we call technical debt, which is a very common term used in the software industry. What I mean by technical debt is basically when you're given short deadlines, business pressure, for example, you might be not having much time to write enough test cases or consider other factors such as good code quality. So you might end up rushing documentation. You might end up not writing code in a proper way. So in order to prevent that, in order to prevent extra technical debt, you should follow good coding practices. Yeah. So the next part is basically talking about refactoring. So what refactoring means is that it is not essentially just rewriting the entire code, but to look at places where the code architecture can be further improved. So improving code structure can also help you verify bugs that you might have unwillingly written into your code. And it helps improve performance because you're able to test more throughout your code by increasing your code coverage. So where you should refactor is basically you should strive to refactor by writing clean code wherever necessary. So where it is necessary is essentially parts that have been found in your code review. So what code reviews mean, I will illustrate later in the next few slides. Um, During code reviews, we can find cases where the code may not be optimal for the classes that you have written. So what you should do during refactoring is basically that again you must make sure that the code becomes clean, and that what we must make sure is that the test cases that we have written before continue passing even after refactoring. So you don't want a case where you write a new code or you refactor code, but then you start failing the test cases that you have written before. So that's the importance of having good test cases. It will help you verify post refactoring that your code still works as intended. Okay. So how you refactor the code is by following a proper standard. So this standard is pretty much taken from our CS 2103 website, which I believe has been resource indicated to you in part one of the lecture as well. And there'll be some more examples later to show you guys um, where you can find resources on the 2103 website. So some things that you can follow is to name your functions well, avoid unsafe shortcuts, and then you should also comment minimally but sufficiently. Okay, among maximizing readability, there's a lot of points to cover. So in the next few slides, there'll be some examples of how you can do this. So you should first avoid long methods. avoid deep nesting complicated expressions. Magic number strings should also be avoided. And then you should also practice structuring code logically, of which there are some examples such as the KISS principle as well as the SLAP principle, and also following the happy path, which we will illustrate later as well. Okay, so an example of long methods is that when you essentially don't want to have methods that are more than 30 lines of code. So this is the recommended as per the 2103 standard, that you should not have methods more than 30 lines of code. If in case you have more than 30 lines of code, you should try to refactor them, split them into smaller functions. So what the next pointer is about deep nesting. So this is a quote from Linus Torvalds. If you don't know who Linus Torvalds is, he's the guy who implemented Git as well as Linux. So he says that if you have more than 3 levels of indentations, you're basically screwed, and that you should go and fix your program. So it's a common sentiment that you should not have a very deep nested code inside your code base. So what we mean by deep nesting is that this is very common in, let's say, if you take frameworks such as React front-end frameworks, for example, it's very common that you might encounter code that is highly nested deep into the structure. You want to prevent this because it's very hard to debug in the future in case something goes wrong within the levels of nesting. So unlike what you might have seen in other courses, here we recommend you to avoid any level of nesting as much as possible. So this is an example, again, taken from the 2103 website as to what we mean by deep nesting. You should not have this many if statements checking for many conditions. Instead, you can linearize the conditions into a um, singular block without many levels of indentation. And next is the happy path. So what we mean by happy path is that you need to find the execution path taken by your code most commonly. Okay, so you don't want to have an if statement where you check for the path that your code will not take most of the time. Like for example, here it's given the if not is error case, which doesn't occur at many times. More often than not, you're going to go into the happy path, which is to not handle the unusual case or not handle the error case. So you don't want to have such a if statement here, okay, where you look for statements that are not executed by your code often. So this is an example of a refactor where you have a guard clause first to immediately catch the cases where the code doesn't execute much, and then follow up with uh, the rest of the code that is executed frequently. So here we saw if statements nested, checking for the condition of if is usual case or if is error case, while not returning immediately for those statements. Whereas in the good example, we reduce the level of nesting and then return immediately by handling those errors instead of continuously checking for other subconditions. Yeah, so I hope this was clear. If you guys have any questions, you can ask me after the lecture about this. Yeah. Okay, next is avoiding complicated expressions. So complicated expressions are usually the case where you try to linearize the statements that you have. For example, the return statement here, it combines 3 conditions together in a singular line. We typically don't recommend this because it is difficult to debug this sort of case. So what we recommend instead is to have multiple Boolean conditions, checking for whether each of these conditions are true or false, and then combining them in the final return statement. So next is the avoiding magic numbers. So we don't want magic numbers such as a floating number such as 3.14236. We would rather have them named as static constants in your code instead. So for example, if you know you're going to use 3.14, you can replace it with the static final double variable over here and call it pi. and then reference pi for the rest of your code. Yeah. Okay. Uh, Also, you can have avoid magic strings. Like for example, your return 4132 is a magic literal. So you don't want to have numbers hanging like this. You would pretty much want to again use the case before where you would label the variable that you're going to use and then return it immediately as the variable instead of using numbers or strings. Okay, the next thing is to make the code obvious. So, in making the code as explicit as possible, you should try to use parentheses, especially for Java, where you might have single line statements where you can immediately return, for example. I know there is a syntax in Java, for example, if you use the if statement and there is one conditional followed by a single statement after it, there is no need to put the braces, but we recommend against that for you guys to use the braces instead. Yeah. Next is to structure code logically. So in this case, you should use blank lines to group related statements together. For example, if you have a bunch of code that is relevant to a particular function, you should make sure that they are contained within the same block, and then you would give some spaces followed by the subsequent code after that. So this is basically to give you some sort of a logical structure to the code. The next part is to not trip up the reader. So we don't want to use parameters that have been unused. So a common thing to do is that after you write your code, if you check any unused parameters, you should delete them from your code base. A couple of other points to note is that you should if things are different, then you should label them differently. You should not try to force the naming to be similar if they represent two completely different things. Another thing to note is not to have multiple statements in the same line. We recommend one statement per line. Okay, the last few parts for the implementation is to look at some principles that we follow. So the first one being the KISS principle. So keep it simple. Basically, it's an idea where you should not dismiss the brute force methods in favor of a more complicated version of the same code. So if there is a way to do things simply, you should take the simple path and write simple code instead of forcing artificial forms of complexity. The next is to avoid a premature optimization. So again, you don't want to write complicated code that is highly optimized for a particular structure. You should make it, you should add redundancy as much as you can and avoid premature optimizations. So what we mean by that is if in any case you are having statements that can be condensed into a single line, it might be useful for compiler optimization, but we don't recommend that. We recommend you split the if statements up into different chunks and blocks, as demonstrated earlier. Another principle is the slab principle. So slab basically refers to a single level of abstraction. So you should not have varying levels of abstraction. What we mean by that is here you have an example of your salary and tax, as well as a read data method. So in this case, you are calling multiple functions and you're aggregating the results in this function over here. You don't want to perform calculations in this function where you are trying to just aggregate results. Instead, we recommend moving the salary and tax lines to a separate function. And then under this function that you're going to execute the aggregation, we should just have three function calls, three clean function calls instead. Okay, the next thing is to follow a clear standard. So what we mean by following a clear standard is that you should set a standard between you and your partner for Orbital that you're going to follow for the rest of Orbital for your code base. For some examples of this is that Naming styles are a good example. So whether you're using Pascal scale, camel case, or snake case, would be relevant. So in case one person uses a camel case, you should standardize camel case throughout your code base. So another thing is that IDEs nowadays have their own tools for you to help you do this. So you can make use of those tools to make your life easier as well. Um, as covered earlier, you should name your functions well. You should name your variables well as well, in order to improve the readability of your code. Uh, Basically, this will reduce the ambiguities as to what that function is supposed to do or what that variable is supposed to represent. So a common example of naming is what is a good class name and what is a good method name. So usually names such as a check limit is a bad naming as well as a result because they don't clearly tell you what they're doing for result, for example. So instead of result, you should have something that tells you what it actually means, such as calculate. And then for check limit, a better version would be a limit checker to indicate the actual use of the function. So another use case for single valued versus multi-valued variables is that here we have a singular called student, and then it's of a type person. Uh, the next is you have your person variable, which is a singular student, as well as the array list with multiple students. So in this case, since this is plural, you should use the students instead of a student. So this is an example of a multi-valued variable where you would use the plural form instead. The next is to use the standard words. So standard words meaning that you should spell stuff correctly. Again, I think IDEs have tools to make sure that you can do this well. So I won't delve very deep into this. Yeah. Next is using names to explain. So instead of something simple such as a process input, you should try to have a method where it's quite clear what you're trying to achieve with it. For example, remove white space from input. And instead of a flag variable, which is commonly used for checking whether something is true or not, you should use is valid input if you're checking whether the input is valid or not, in order to make sure that the intent is clearly communicated through the naming of the variable. Another example is by size order versus order by size. This is a sensible ordering of your verbs and your nouns within your method names. So again, is the not too long versus not too short. So it's preferable not to have lengthy names. So names that are too short, for example, may not be sufficient to convey the message behind the method. And the next part is to avoid misleading names. So misleading names, meaning that what we mean by color black versus color blue versus color white. So instead of using uh, color blue or color white or color black instead, because these are essentially enum types of the same type, we should instead for use hex for black, hex for white, hex for red to indicate the actual use of uh, these variables. Uh, the next part will be to avoid misleading, ambiguous, or similar sounding words. So we don't want to use words where they are essential short forms of the actual things they're trying to convey. So for example, instead of using numbers in your variable names, we recommend you use words to indicate them instead. So instead of phrase zero, you should spell it out. Yeah. Next, you should have stuff that is easy to pronounce, ideally, as well as using simple terms such as egg instead of filet mignon, for example, when such complexity is not required. The next part is to avoid unsafe shortcuts. So you should use language constructs in the way they're meant to be used, even if the language allows shortcuts. Um, so some examples are using the default branch. So in this case, if you have a switch type and multiple case attributes versus the default, you should always have a default switch type here to indicate what the path should be taken in case all the cases fail. Next part we will cover is recycling variables or parameters. So in this case here, we should have, it's preferable to have intermediate variables for computation and then returning the final variable uh, in this sort of manner instead of inlining everything and using the parameters and computing, reusing the parameter names instead. The next thing is to avoid empty catch blocks. So whenever you have a catch statement, try not to leave the catch block empty. Or if you leave it empty, give a comment to explain why the catch block is empty. And you should also practice deleting dead code. So dead code essentially can be picked up by the IDE sometimes and sometimes by the compiler as well. So in any case, if there is going to be code that is never going to be executed, you should ideally delete it in order to increase the readability of your code. Uh, then I guess the last part is to minimize the scope of the variable. So if you have variables that doesn't need to be global, please make them localized within your function. For example, this will avoid the number of overheads that you have and also avoid confusion in case you have multiple global variables that are taking the same namespace. Next, you should also avoid a code duplication. So the main reason why software engineering principles are so important is we want to, as much as possible, prevent code duplication. So in any case, if you find that you're repeating code, you can try to make functions in order to reduce code duplication and importing those functions in other parts of the code. Comment minimally but sufficiently is one important part. So you don't want to have a lot of comments in your code that obstructs readability, but at the same time, you do want to comment sufficiently within your methods to make sure that people understand what you're doing. Uh, The next is to not repeat the obvious. So this is an example where you should comment sufficiently but not over comment. So like for example, x plus plus this, it's quite obvious what it's trying to do. So you don't need to add a comment to it. Same for the method called trim input. It's quite obvious that it's trimming the input. So this sort of comments are not required. The next part will be to write to the reader. So you should not write comments if they are private notes to yourself. It should instead be a JS docs version where, or Java docs version where you communicate to your fellow teammate or fellow developers as to the true use of the function itself. So here is an example. You should not use words such as a quick trim function used to fix bug I detected overnight. So it should not be something that it's focused on you. Instead, you should be focused on the function itself and trying to explain what the function does. Next is to explain the what and the why, but not the how. You should leave the how generally for the explanation for the code works to the code itself to do the explanation. This is why we recommend you having good method names and good variable names so that the variables and the methods do the explanation themselves. So what you should be having in your documentation is pretty much the what and the why instead of the how. So here is an example of what I mean by having the what and the why, but not the how. So here, this is an example of explaining how the code works. Essentially, we don't want to have comments explaining how the code works because that's quite obvious. You should have refactored the code to indicate how the code works because it's we expect it to be quite self-explanatory. Okay, the next part is for quality assurance. So we will be looking at testing as well as test case design. So why quality assurance is important is because it is a mixture of validation and verification. So validation is basically asking the question, are you building the system the right way? And verification is, are you building the system right? So essentially, there is a small nuance here when it comes to validation versus verification. So the first part under validation is static analysis. So you should essentially, static analysis is what you do when you analyze the code for static errors, such as unused variables, unhandled exceptions, stall errors, and other forms of statistics that can be derived from your IDE, for example. So most modern IDEs have some sort of inbuilt static analysis capability. So for Java, I believe you might have seen the Java check style. So this is a IDE implementation of static analysis that helps you catch dead code, for example. Uh, the next part I would like to cover is code reviews. So I will give you an example of what a code review means later, but essentially it is uh, two people who are working together. One person publishes the code while the other person reviews the code. This sort of process can detect functionality defects that can be present in the new code that one developer wrote. And it can also verify non-code artifacts and incomplete code that might be inside the code. So this is an example that I've attached here as a simple checklist as to how you can perform a proper code review. So some things to take note of is whether the code is clean or not. So the first part is to check if you have removed all the debugging artifacts. The second part is to ensure the code hygiene to make sure if you have duplicated any code. Third part is to make sure that your code review description is well and contains all the parts required over here, which I'll cover soon. And the last part is to check if there's any documentation required. And if there's any documentation, you should have already written it within your code itself. And the last part is to check if there's any follow-up tasks or any other tickets that need to be solved together with this follow-up task. So in the PR description that I've shown here, there are some examples as to what you should include in each section. So when you create a pull request, you should essentially have the problem that you're trying to solve, the solution that you have recommended to solve the problem, as well as the approach that you have used. The next part is of course, testing. What level of testing you have done to verify that your implemented solution works as intended. And the last part is any consideration related to any document or any follow-up ticket that might need to be resolved together with this pull request. Okay, so this is quite a large slide where I would like to briefly talk about web and mobile development, uh, a system design consideration that might be present within web and mobile development. So this is a inclusion that we have made in the past in this year for this year's software engineering slides, as to give you guys more context as to some design patterns that are involved in modern architectures that are not present in so-called general software engineering. So when it comes to web and mobile development specifically, there is this very popular debate on the REST API versus other forms of API such as GraphQL versus gRPC. So what the REST API is essentially what you see here in this example, where you have an endpoint. You basically indicate the HTTP method you're going to use, as well as the headers that you're going to accept and the body of your request. So this essentially is the common structure for a REST API. So the REST API essentially uses a get, post, put, and delete, and is basically a very resource-oriented approach. And it's the most widely used architecture in modern web development. Although this has some drawbacks, which can be addressed by alternative API implementations. such as GraphQL as well as gRPC. So an example of GraphQL is given here where you essentially query only for the stuff that is required for your API. So why GraphQL is better than REST API in some cases is because you prevent overfetching, because you essentially only indicate the methods and data that you require. So you kind of make it implicit to the GraphQL interface while requesting for new data. So this prevents multiple fetch cycles that may be present in REST APIs where, let's say if you click a button, there might be multiple requests made to a REST API endpoint. Whereas for GraphQL, there are methods that are inbuilt to prevent multiple network requests to fetch the same data again and again. So this GraphQL interface essentially minimizes overfetching, which is the main uh, plus point when it comes to GraphQL. So the last part is gRPC, which I do not have an example here as of now, but I'll briefly explain what gRPC is. It is a remote procedural call interface that is implemented by Google, and is essentially an action-oriented design where clients implement server methods like local functions, and the transport protocol used is not uh, similar to the transport protocol used in REST API. Um, this is a much simpler transport protocol where only the sufficient headers are being sent over. You don't have complex HTTP headers as required in REST APIs. So what this means is that essentially you have 5 to 10 times faster queries using REST compared to REST or GraphQL in gRPC due to the different transport protocol being used. And with a different transport protocol, it also comes with binary serialization, which is a simpler algorithm compared to what's implemented in REST as well as GraphQL. And the most important implementation that uses gRPC is basically your bidirectional streaming capabilities for, let's say, robotics, for example, that use bidirectional streaming between two endpoints. Okay, so that's basically one slide talking about for example, the design considerations that you would make in web and mobile development. So for now, we will come back to testing once again. So for testing, we will talk about the software under testing section, where essentially you talk about executing a set of test cases for a particular method, for example. So how you should do your test cases is that you should feed your input into the software under test. You should observe the actual output and then compare the actual output versus the expected output. So this is essentially the same as having a bunch of test cases written and then comparing and asserting whether the outputs of the methods match what you expect. So a most common form of indicating whether you have implemented test cases correctly is testability. So testability is an indication of how easy it is to implement your software under testing. So there are various forms of testing types, which some of which we will cover today. Unit integration, system testing, developer, alpha, beta, and regression testing. So you might want to include this in your milestones because it is for Apollo as well as Artemis. It is expected that you guys do some form of testing. So these few slides will be quite important to illustrate how you can perform testing. So unit testing is when you test individual units in your functions in order to make sure that each piece of code works. So what we mean by this is unit testing is mostly function-based testing, where if you have a read function and a write function, you would implement test cases to verify the behavior of the functions individually for how read works as well as write works. So here is an example of the implemented test harness for the full test class, where you essentially test the read method, the write method for whether it throws an exception depending on the input that it receives. Okay, the next part is use stubs for unit testing. So stubs is the most common form of testing framework that is used to make sure if your test method works as expected. So stubs essentially mean that if, let's say, your full class requires dependencies from other classes that have not been implemented yet, or if you like to test the foo method in isolation, then what you should be doing is to list down those dependencies in those other classes and then implement what we call stubs for them. So stubs essentially mean that they mimic what the class is supposed to be, the other dependencies, but they don't fully implement those other classes. So this is an example of limited software under testing where you essentially only want to test this full class and you isolate it from other classes that you have implemented. So for those other classes, you implement stubs instead. So here is an example of a stub, as I was saying earlier, with a different class here called the logic class. You have the class here called logic, as well as the interface called storage, as well as a class database storage that implements storage. So here, if you take a look at these methods, we will basically look at how to implement stubs for them. So normally you would use the logic class as follows. So you should, depending on the new database storage, to perform the get name operation. So what you are essentially doing is you are having a new logic class, and then you pass it the new database storage instance. So you see here that here we create the new database storage instance from here. And then we have the new logic class that is created from this class over here. And then you would use that to get, you would call the get name method on the logic instance and pass it this variable 23. So what we mean by isolation testing is, if you want to write a test case for the get name method, right, you should isolate the dependency here called the database storage dependency. So here you will see a new logic class that takes in the new database storage. So this part remains the same as what's being implemented here. But here you should essentially have an assert equal statement to say that the name John is the same as the logic.getName. So this is an example where you only test for this getName method in isolation, whereas you keep the logic of the other dependencies the same by having this over here. So if you want to implement a stub class for this, you can essentially have a storage sub that implements storage. So for example, here in this interface, you're not quite sure how it works because it's a blank interface and you would like to, again, test this logic class in isolation. So the way you would do it is you would implement a storage stub, which implements a get name stub method. And then under the get name method, you would essentially once again have this test class here where you would instantiate the new storage stub instead of what we see here, the new database storage. So this is what I meant by isolating dependencies. So here, if you have the database storage dependency, you would essentially replace it with the storage stub here and replace it with the new storage stub class. Okay, so the next part is integration testing. So you should basically test if other whether parts of your code work together when you put all of the code together. Meaning that, let's say if you have a singular class called a car that uses an engine and a wheel. So if a car assumes a wheel, it can support a speed up 200 mph, but the wheel can only support a speed up to 150 mph. So this is an example where um, you would need an integration test to figure out if this thing actually works as expected, meaning that you would basically integrate the car class together with the engine and the wheel class together. So here in the unit test example, you saw an example where you would test this logic class and its function called getName in isolation by implementing this storage stub. But here in integration testing, we don't want to write stubs. We would want to have the class itself, for example, this database storage class implemented in full, because we want to assess how the entire system works together. So an integration test is basically, as I said before, it's not the case of repeating the unit test case, but actually to take all the dependencies together and test all of them in tandem. So a system test is when you test it against a whole specification. So for example, you should go beyond the bounds defined in the specification. So for example, suppose that the SUT is a browser that is capable of handling web pages contain up to 5,000 characters. So here is a test case to test if the software under test fails gracefully. So what we mean by this is you essentially have a test case where you should test if the load web page is too big or not. And then based off of that, you basically have the input, which is loading the web page, and then the expected behavior is to test how long it takes to load the web page. So this is an example of system test where you place the entire system under some sort of load. And usually system tests tend to be load testing. So for example, here you essentially do a load test under many users, or you load test with a lot of components integrated together. So system testing basically includes testing against your NFRs. So what we mean by non-functional requirements is requirements that are outside of your typical testing functionality. Like for example, your typical functional requirements tend to be whether something works correctly as expected. So functional testing is uh, your integration testing as well as your unit test case here, where you're testing whether your functionality is as expected or not. Whereas for system testing, you are testing non-functional requirements, which usually mean like performance testing, load testing, security testing, compatibility testing, usability testing, as well as portability testing. So what these mean is that, um, so for example, load testing here is also called stress testing, meaning that you would place the software under heavy load, meaning that you would have many users using the website at the same time, for example, and then you would see if the website is still responsive or not. So that's an example of a load test. So security test, an example of a security test is, for example, a SQL injection, where you test if different forms of inputs into your website still function as required and don't break the website. And other forms of testing is usability testing to check if how easy the system is to use, as well as portability testing to see if, let's say, your software works as correctly under Microsoft Windows operating system. You would want to make sure that it works well in a Linux environment or a Mac OS environment as well. So you should test if it works well on different platforms. So other forms of testing that we will not cover in detail today, but it's listed on the 2103 website in case you want to take a look at it, is basically developer testing, alpha, beta, as well as regression testing. So developer testing is essentially the developers themselves trying out the platform and seeing if all the functionalities work well or not. The next few cases is the alpha and beta testing. So alpha testing and beta testing is basically a test performed by the users under control conditions, whereas beta testing is the same thing but by different forms of testers that are not the developers themselves or the users, the primary users of the platform. So you might heard of beta testing in other software implementations where the developers are trying to get feedback on how good the software is. The last part is regression testing, where if you modify a system, the modification may intend in some unintended and undesirable effects on the system. So we basically implement regression testing to make sure that we retest the software in order to detect any forms of regression. So regression testing is especially useful if you have multiple versions of the same code base and you're, let's say, deploying the code base to production, for example. You want to have regression test code to make sure that nothing is broken while pushing the code to production. So a brief introduction to test case design. So how you should design a test case. So you would want to think about how your users would use their platform or how the developers would use the function, and based off of that, come up with different ways to structure your test cases. So here, consider a test case for adding the string object to a collection. You should test if all edge cases have been handled. Like for example, if you add an empty item to a collection, whether that is handled, whether and adding an item when there's one item in the collection works fine, and adding an item when there's two or three or n items in the collection, adding items that are in different languages, for example, adding an item that is already an existing item, adding an item that is immediately after adding another item, or adding an item immediately after system startup. So these are various scenarios where the simple add item function could possibly fail, and you should cover all bases by testing all forms of edge cases. So test case design is essentially the cost of testing. So in some systems, a single test case can cost thousands of dollars. So we want to make sure that we use the best use of testing resources. So testing should be effective and testing should be efficient. So for testing to be effective and efficient, each test case that you add should be targeting a potential fault that has already not been targeted before by existing test cases. So here is an example of a positive versus a negative test case. So a positive test case is when the test case is designed to produce the expected behavior as you expect, whereas a negative test case is to assert whether uh, there is an invalid behavior in an unexpected situation. So here is an example of a positive test case where you have a method called print integer I that takes in the argument integer I. So a positive test case would be to make sure that I equals to a new integer 50. So this is a positive test case because this is the behavior that you would expect by having the correct input that is inside the print function. A negative test case is an example where you would expect uh, a type that is not similar to the return type of the print statement. So here you would expect this test case to fail, which is why it's called a negative test case, because you would expect the test case to fail. Here you would expect the test case to pass, so it's called a positive test case. So the way you should basically try to figure out all the edge cases for the test cases that you have is by mainly two methods called equivalence partitioning as well as boundary value analysis. So equivalence partitioning means you should check if is valid month. For example, if you have the is valid month method, it returns true if m and int is in the range of 1 to 12. So let's say this is our method here. Sorry, the test here, for example. So this method here is inefficient and impractical to test for all integer values. So there is no need to test for all possible input types. So in general, most software under testing doesn't require you to test every single edge case. Instead, you should test groups of test cases that have been grouped together. So you should have a range of inputs that are treated in the same way under each equivalence class. So we will see an example here. So I'll skip this slide. Okay, so here is an example of the equivalence classes that we can use for this method here. So take a look at this, where if you have if m is an integer and it must be within the range 1 to 12. So a possible way we can structure the equivalence classes is first to check if you have inputs between minimum integer and 0. So this is below the range it is expected to produce false. So 0 is the left boundary of 1, as well as minimum integer is the minimum possible integer that can be represented in the system. So min into 0 would be the left boundary of this test case. 1 to 12 is the positive boundary of this test case where you essentially expect the function to produce true. And then 13 to max int is the right boundary of the test case where you expect the function to produce false. So you basically cover all three sets, the left boundary, the main boundary itself, as well as the right boundary by checking all forms of inputs. So here is another method called the is prime method. where it takes in the integer I and returns true if I is a prime number. So the equivalence class for this could be, first I could be prime numbers that you expect to produce true, and then the non-prime numbers which you expect to produce false. So here in this case, we only have two equivalence partitions. So important thing to note is that each equivalence partition cannot have the same values as stated here. If you have one group of values here, in one particular equivalence partition, you expect it not to be repeated in the other two partitions. So an example of equivalence partitioning is that some inputs only have a small number of possible values. So you should, in those cases, you have to consider each value as a partition itself. So let's say if you have a method show status message that takes in the game status S, that returns a unique string for each of the possible values of S. So for example, we are assuming here that game status is an enum. In this case, you should test all possible values of S that can be considered as a partition. So let's say, for example, game status has 5 enum types. You should test all 5 enum types. And each one of these enum types will be your equivalence partition. So your equivalence partition is merely a heuristic and not an exact way to test the function, meaning that it is a prescribed way by 2103 to do your testing, but this is not the end-all be-all sort of method. The next type is boundary value analysis. So what we mean by boundary value analysis is that it's a design heuristic that suggests when picking test inputs from an equivalence partition basically indicates what values are important to be tested. So we essentially analyze boundary values. So for this example here, a boundary value could be 0 and 1 or 12 and 13. So these are examples where the test changes from true to false or false to true. So essentially these become your boundary values. So typically you should choose 3 values from the boundaries to test. One value from the boundary itself, one value below the boundary, and one value above the boundary. So here, as stated before, if your equivalence partition is 1 to 12, then some possible test cases would be to choose 1 and then to choose 12, right? 0, 1, 2 could be one set of boundary values that you can test, and 11, 12, 13 could be the second boundary that you test. Basically, the right boundary of the equivalence partition and the left boundary of the equivalence partition. So same for the rest, which I won't cover in detail, but you can take a look at it also. Okay. Okay, the last part is to cover documentation, which is basically talking about your README file. So in your README, your task should be to include, to first describe and justify your design properly. The second is to explain the testing. And the third is to discuss any SE principles and practices in the code. So the first part I'll cover is the design. So in the design, you should take note of your use cases and your features that you want to put inside your README, the flow and architecture, design diagrams that can be drawn with tools such as maybe like draw.io is the most common one I've seen, design patterns and principles, as well as design decisions. So here's an example of what we mean by a good activity diagram. So here we have an activity diagram that states what happens after you enter the login or register page. What happens, whether you enter the user profile, what you're able to do under the user profile, which is basically edit your user info. So this basically gives a directionality of how the website operates. So it's a good diagram because it illustrates every possible case after the user enters the website. And below underneath, we see a description of how each of these individual components work. So in your README, please make sure to include your activity diagram. So a diagram that is suitable to describe the architecture, as well as explanation for that architecture. So the next part is to include some testing, as well as your testing pipelines that you have employed. So let's say if you use the unit test cases as well as, let's say, developer testing, you would want to put that in your README and include that over here. So here is an example from a previous orbital project where they implemented automatic regression testing. So here is an example where they have an automated regression testing plan where they use the XML paths, they target the XML paths of the fields, and then based on that, they have an automated testing system. Okay, next is the software engineering practices. So if you're under Artemis, you'll be expected to follow a 2 week sprint every sprint. For Apollo, there is no requirement to follow a 2 week sprint, but it's recommended that you still follow it in any case to make sure that your features are coming along and that you have enough features at the end of orbital to qualify for the 6 to 8 features for Apollo. For Artemis, it's 9 features or more. And for Gemini, I believe it's 3 or 4 features. So in order to make sure that you deliver the number of features that you require, it's expected that at every sprint, you deliver the number of features that is planned as per your plan that you might have between you and your teammate. Okay, so that pretty much concludes our lecture for today, which is talking about the first part of the software engineering practices were to talk about requirements, project management, design. And today we covered more of the implementation, quality assurance, as well as documentation. Yeah. So yeah, that comes to the end of my presentation. If you guys have any questions to ask, you can feel free to stay behind in the Zoom call and ask those questions. Else you can feel free to leave. Thank you for coming. Okay, I assume none of you have any more questions. If not, I'll just end the call. Okay. Thank you guys for coming.